Hello, this is the first meeting of Physical Sciences for Elementary Education 102L. This is a recorded lecture, so you can watch it as you like. Skip ahead if it's boring, or go back and see other parts again if you want to see them again. This is what used to be called, what is still called a flipped classroom, in which you listen to the lecture ahead of time at your leisure as you like. And then at the recorded lecture time, which for us will be Monday at 3:20 p.m., every Monday, 3:20 p.m., I'll open up a session, a WebEx session or a Zoom session, in which you can ask all questions. We can discuss all of this material in a synchronous mode. So this is the asynchronous. That is to say, I recorded at one time and you listen to it at another time. It's asynchronous. So this course is also known as Physics 102L or Chem 102L because there are two components. This course was devised by Kathy Burke in the chemistry department and by me in the physics department. We've taught it for some time. And so this is the beginning of this semester. We've never taught it online before. There will be snags and difficulties. Please be patient, okay? And if you find suggestions for us, please give us those suggestions and we'll do our best. So this brief introduction, we'll have a syllabus. We'll discuss the syllabus a little bit, which is posted on Canvas, so you can read the whole thing. There's also, I've included a STEM education link about the importance of STEM education. So STEM stands for Science, Technology, Engineering, and Mathematics. Okay, and and then I'll follow this introduction of the syllabus with the beginnings of the first week of the physics part, which is measuring mass and length. So here's the first page of the syllabus, the first half page of the syllabus. And you can see that both Kathy Burke and I have our office addresses, our ISU email addresses, and our telephone numbers here. And later on, I will say that you can contact us at any time because we're here for you. It's really true. The course contact and the course scheduling people in the physics department are listed here. Now, since there are two parts, there's going to be a chemistry part and a physics part. And so the required text for the physics part is a textbook that was written by E.J. Bong in the School of Education, where most of you are from, and by me. It's called Children Doing Physics: How to Foster the Natural Scientific Instincts in Children. So it's a way of teaching physics, which me, as a practicing experimental physicist, find to be important. Okay, and it's the way children really learn physics. Both boys and girls learn to like physics and to like science by actually doing it, even as children, even in elementary school, by building things and by making things and measuring things and seeing them work and coming to an understanding. Now, this book is not too expensive. We tried to make it minimum cost. You can go to this website, Cognella website, and just buy what you like. It can be an e-copy, it could be a paperback copy. And let me just hold this up. Here it is. That's what it looks like. And Children Doing Physics. Whoops, here we go. And it's paperback. You can see it's not a hardbound, and it's color. You can see. Okay. So it contains a lot of things. I won't start talking about this textbook now, but it is the backbone of the physics part of this course. But as it says up here, it's also useful not only as a textbook now, but as a future reference as a teacher. It's a guide for what you can do in the classroom, both today and tomorrow. It's good for homeschooling too. And so someday the principal of the elementary school, on a Friday afternoon, you're going out to the parking lot and he says, well, what are you going to do in science next week? Well, you'll have about 48 suggestions, okay, by looking at this book and by paying attention to this course, okay? Now, the chemistry, Kathy Burke will tell you all you need to know about the chemistry. They're posted on Canvas, are files of the chemistry component, textbook and references here. And there's also a very excellent physics textbook by Hewitt and Hewitt called Conceptual Physical Science Explorations. That's in the Parks Library. So all that information is available. You shouldn't have any trouble finding content, shall we say, content information. Now, Physical Sciences 102L is fully online. Okay? All lectures and lab sessions with TAs are online with WebEx. Now, honestly, a few minutes ago I tried to set up a WebEx session for tomorrow, and I ran into all kinds of difficulties, so I set up a Zoom session. Okay, but either way they should work. This is the ISU Canvas site, and as I said before, office hours are anytime you want them. You can say, I'd like to talk to you tomorrow at noon. I say, fine. Set up a Zoom session, we talk. Okay? Now, the idea behind this course is that children, if you watch them play, they're natural scientists. They're really very good at science, okay? So just let them go. Let them play with physics toys. The amount of instruction you give to children will depend upon the grade level and so on, and the appropriateness of the topic and so on. So, so now, in fact, I recently looked at the educational system in Finland. And Finland is ranked as the #1 country in the world for elementary education. Success of the success of the students. Okay, and they actually do something rather similar to this. They let young children play, enjoy themselves, and enjoying themselves, they end up liking it and learning it. It's not as it is in some educational systems. Maybe Japan, for example, is an example of a pretty good educational system, but the students are really burdened down with work and rote learning and so on, and it's not fun. And many students decide not to go into science because it's simply not fun. Well, so we're not talking about just fun, but I mean for elementary school children, but let them play with toys. And as you guide them as the teacher, they play with things and build things and so on. So this whole thing of elementary education is in fact quite important. You realize that almost everything in our civilization has to do with physics, and not all of it, of course, but most of it, like 80% of it. So, for example, the power losses here in central Iowa recently. You live for a week without electric power. Well, it's a very, very different world. So, you know, there are amazingly wonderful things on the horizon for people who are scientifically interested and capable, like travel to Mars or magnetically levitated trains, or how do you get across the continent in a hurry and so on. Our high standard of living, in fact, health and general welfare and so on. All of these are very tightly connected to science, in particular physics and chemistry. Okay, so now your students should be able to do all these things without you actually fully understanding all of the scientific details. In other words, you don't have to be a regular physics major in order to teach children how to do physics, and that's the important thing. So here's a brief syllabus by the week. I won't go too much in this, but you can see week 1 starts today, measuring mass and length. Okay? And let me make, although this is spelled out in more detail in the full syllabus, for the physics weeks, there'll be a video report. And that video report, I'll write a rubric for it and post it on Canvas. But basically, a 5-minute video report, doesn't have to be exactly 5 minutes, it could be 4, 6, or 8. You will in that report, you'll videotape yourself and upload it to Canvas for your TA and for me to read. And the video report will say what you have done, how you've done it, and in addition, how you would adapt this experiment, which you've done, to your future grade level, which may be 1st grade or 4th grade or whatever it is. Okay, so that's a bit challenging maybe, and it may be a little difficult to get that going, but video reports will be something that you could actually show to your students in a classroom to introduce, for example, a day or a week of science work. The 4 weeks of chemistry will be weeks 4 through 7. Here are the topics. and Kathy Burke has concept activities and lesson plans. And then the following weeks are physics. Okay, there are no exams, no midterms in this course. Okay, the totality of your grade will depend upon the assignments. Okay, in both chemistry and in physics. So this following this is the considerations for STEM education, pre-K through grade 3. So this is, you can read this. This is posted. The link for this is posted on the Canvas, and you can read it if you like to. But the question is, STEM has been a very serious, a serious topic, okay, nationally, for actually quite a few years now. Okay, so you can read that as your background information, for example, on STEM education. And maybe there are more references in here for other things. Okay, so what do we do this week? This week is measuring mass and length. So how do you measure mass? Okay, what is mass? Okay, well, first off, you've already measured mass many times without maybe realizing it. You can measure mass by just doing a balance with your hands. I mean, here's some Limburger cheese that has a mass written on it of 170 grams. So you can compare that to a lemon and make a guess how much the lemon weighs. Okay, so that's like doing a comparison. It's not very accurate, depends upon your brain and your muscular system and so on, but that's a way of weighing something. A better way to do the same thing is a teeter-totter. And here you can see that 4 kids weigh more than 1 adult. Okay, and so you can weigh masses with a teeter-totter, just comparing one mass with another mass. Okay, and when you do this comparison with your hands or on a teeter-totter like this, you're measuring what's called the gravitational mass, because it's the mass measured by the force of gravity. Okay, and I'll discuss what the force of gravity is in shortly. Okay, so here's the diversion on gravity. Now, let me say in this next 3 or 4 pages or slides, and in future videos like this, I'm going to get into some detail. And so you can kind of tune out if you like, or go get a drink of water or something. And so, because this is not a hard course in physics, so you have to memorize formulas and solve problems. That's not this course. But I want to do a diversion on gravity to describe what it is, how this teeter-totter works. What is the force of gravity? Where does it come from? And so on. So that's what I'm going to do now. Okay? So here you go. A diversion on gravity. Well, gravity, as written here, is a direct force between 2 masses. 2 masses, there's a force between them. And the force is given by a rather simple formula. Actually, it's a simple formula. The force is some big number g times the mass 1 times the next other mass divided by the distance between them squared. And so here's a picture. 2 masses here, separated, their centers are separated by distance r. Those 2 masses feel a force of attraction. Okay, and the force is given by this formula. Okay, so you can put the masses in as so many pounds, and the distance in as so many feet, and then the force will come out in, well, the masses should be actually slugs, but in any case, then the force comes out in pounds. Okay, so, and g has some particular number. So here's for these 2 dogs, there's actually a force between these 2 dogs. Okay, it's very, very small force, and you can't feel it, and because gravity is actually quite weak. So g was actually rather hard to measure. It was finally measured by Cavendish, and a rather elaborate experiment here. He had an isolated brick room, and inside of it he had 2 very massive lead balls hanging from thin wires and silk threads and so on. And when it was very quiet and coaches were not galloping by on the street, things were quiet enough for him to measure a very, very small deflection. So what's in that drawing on the left is sort of shown on the right. There are 2 huge massive balls, capital M, and 2 small masses, little m, on a rod, and then they're held by a silk thread. Okay, and as the little m's get attracted to the big m's, this bar twists just a little bit, just a little bit. And he measured that by reflecting light off of a mirror. And he could see by looking through a little, you can see on the left, by looking through a little telescope into this rather dark chamber, he could see a small deflection of that reflected light beam. And by that he measured G. So, and because he measured G, basically now he measures the Earth, okay? Because in the formula up above, if you know one of the masses, which for example is your mass, then the other mass is the mass of the Earth, okay, in measuring your weight. And so he called his published paper was weighing the Earth. The photograph on the right is actually a modern experiment to measure G with lots of copper. Copper has very high density, very massive, and so on, and very delicate, okay, so that's measuring G. Now, we usually don't use this complicated formula to measure our mass. When you step on a bathroom scale or in the gym, you step onto the weight. I'm sorry, the balance. Okay, the scale to measure your weight. We don't use this big formula. Okay, because we happen to be on the Earth. The Earth is a big mass, and we happen to be the distance away from the center of the Earth is the radius of the Earth. So this formula here. This formula here. 1 second. Okay, this formula here can be simplified by separating out everything but the little mass of the person. So here's a picture of the Earth. It has a mass m. You can consider it concentrated at the center. The radius of Earth has a radius r sub e. So the actual force equation is the mass of the Earth times your mass, and you're on the surface of the Earth, your distance of r sub e away. And so you can factor out your mass, the little m, and all the rest of it becomes little g. And that little g has a name. It's called the acceleration of gravity. Okay? So the force on you standing on the surface of the Earth has a very simple form. It's the force on you is your mass times g, little g. Okay? That's it. Simple as that. Now, and we just use that. And g has a value of about 10 meters per second per second. 10 meters per second squared. So it's quite simple now. Now this is another aside, not very important. The Earth is not a perfect sphere, so the acceleration of gravity depends upon where you are. Here's a British drawing here. If you're on the North Pole, you weigh a little bit less, or excuse me, a little bit more than if you're on the equator or in the UK. So you see it doesn't change by much. It's 9.83, 9.81, 9.78, right? They're really quite close. Okay? So, the meaning of this acceleration of gravity is that when you're falling under gravity, so you're in free fall near the surface of the Earth, your velocity increases by 10 meters per second every second. So in the first second, after the first second, you're traveling 10 meters per second. A second later, you're traveling 20 meters per second. And then you're traveling 30 meters per second after the third second, and so on. So that's what the acceleration means. Acceleration means your velocity is changing. In other words, here your velocity is getting faster and faster as you continue to fall. Now, so that's an aside on gravity. Now, in a regular classroom or lab, you would have access to a standard masses. But here, we don't have a set of standard masses to send you. We send you many things in a box, but we didn't want to send you heavy masses. So we'll make our own. Now, making your own is always a good thing to do, especially with young students. Okay, you can get them together and they can start to make standard masses. So here, if you open up your folder for weeks 1 and 2, also includes week 3, open up the digital mini scale, you'll find this, okay? And there's a battery component in the back. You have to take the plastic wrapping off the batteries, okay, and reinsert the batteries. Then when you touch the on-off button here, it'll boot up, so to speak, and it'll read. Why is it taking so long? You have to hold it horizontal or something. Yeah. Okay. Now that's embarrassing. It should read 0.00. Okay. and it's doing something funny now, and I don't know why. So in any case, this measures in grams, or you can go to, you can go to ounces too, and so on. And so this is a very accurate scale. Okay, it measures down to 0.01 grams, and a gram is actually quite small. A gram is 3% of an ounce, for example. Now, at the suggestion of Paul Herrera, one standard masses we can use are coins. So, for example, get some quarters. American quarter, has silver and copper in it, I guess, and it weighs so much. You can weigh 1 quarter, and if you have several quarters, weigh them all, and put them in a table. So that's what I did. I took 10 quarters, measured them one at a time on this, and I recorded the mass of each gram, and recorded it in a notebook. Okay, so this is what maybe I'd like you to do. Here's the first page of the notebook, and in here I have the quarter number. I have 10 or 11 actually. I measured, and here's the mass. The first one had a mass of 5.66 grams. The next one had a measured mass of 5.74 grams. Not the same, right? 5.73, 5.65, and so on. Okay? Measure them one at a time. Now, you're not surprised that they're a little bit different. Not much, a little bit different. Well, because some of them are old, some of them are new, maybe some have something stuck to them, and the other ones have some rubbed off, and so on, and so they're not all identical. Okay? So, what I did then is let's go to the next slide here. I made measurements of 11, and there's a cluster here, of masses around 5.7 grams. Okay? And so with my eyeball, I estimated where the average of this cluster is about 5.68 grams. So I think a quarter weighs about 5.68 grams. Now, however, one of them I measured, number 11 actually, is 5.38, which you can see is plotted here. And it's an oddball, okay? It's a real outlier. It's absolutely not a part of this population here that has a mean of 5.7 grams. And you take a close look at it. It's not a quarter, okay? It's a Korean coin, which looks a lot like a quarter, but it's not a quarter. Now, this distribution, so you see there's a string of numbers here. I could have measured 100 quarters, but 10's enough, okay? And this plot here is what's called a histogram. There's an axis here, which is the mass in grams. The tick marks of 5.3, 5.4, 5.5, 5.6, 5.7, and 5.8. And then I divided it up into half of that spacing. So, for example, take 5.6. There's a vertical line at 5.6. There's a vertical line at 5.65. And then at 5.7. Okay? And so you look through your numbers, and you take each number and ask what bin does it fall into. So the first one, 5.66, falls into this bin here, the bin that has 5 entries in it, because here's 5.6, that's 5.65, and 5.66 is inside this bin. It's between 5.65 and 5.7. So you take all of those and put them in their proper bins, and this is called a histogram, or a frequency distribution. It's extremely useful. First off, you can see all the quarters are rather tightly clustered around 5.68. And even with your eyeball, you can estimate what the average is for these 11 measurements. Okay? You can also estimate what the error is. The error is about a bin or half a bin. In other words, you can move up and down by half a bin, and there's still some quarters in there. Okay, so that's the chapter, appendix. What is it? Appendix, it's up here, Appendix B of your textbook, actually, discusses a little about statistics. So statistics is a name that's given to the analysis or understanding of collections of measurements. And statistics is actually quite powerful. It's very useful to understand a little bit of statistics, okay? especially when you're making multiple measurements and so on. Now, so in estimating the 5.68 grams, I did that by eye. I didn't use a calculator. I could easily have taken a calculator and added up all these numbers and divided by 10. I should do that, but 5.68 is an eyeball estimate, perfectly good. Okay? And, okay. Now, the thing for you to do is to measure, get all the coins you can. And the mass of a quarter here is 5.6, well, 5.69, I put it down as 5.69. It should have been 5.68 actually. And then you can measure the mass of a dime. So you measure all the dimes you have, get the average, 2.28 grams. But look at the mass, and well, let's go on. Now the mass of a 50-cent piece is 11.21 grams. And the mass of a dollar is 22. I only had one. It was an Eisenhower dollar from a long time ago, actually. Mass of 22.77 grams. Okay, those are the masses of the so-called silver coins. Okay. If you take, for example, take the dime, it's worth 2.5 times less than a quarter. So if you take the mass of a quarter, divide by 2.5, you get 2.28 grams, which is just what the mass of the average mass of the dimes I had to measure. Okay. A 50-cent piece is worth twice a quarter. So if you take the mass of a quarter and multiply by 2, you get 11.38 grams, which is close enough to 11.21 grams. And a silver dollar, is worth 4 quarters. I have times 5 here, but I really meant times 4. It's a mistake, excuse me, times 4. Is 22.76 grams, which is very, very accidentally close to the measured value. So you see the mass is proportional to the value of the coin. And that's true for the silver coins, American silver coins, also European, by the way. Pennies are zinc plus copper, and nickels are copper and nickel. Okay, so they have different masses. Okay, but the silver coins, the value of the coin is proportional to the mass. Okay. So now you can make standard masses from this. You can take 10 quarters together and you have a mass of 56.9 grams. You can add in another coin or so, maybe a penny, and you can get it up to an even 60 grams if you want to. Okay. So now, for example, here's a teeter-totter, which I made from the ruler in your kit. I used a pen to balance it on. And on this side is a silver dollar, and on this side are 4 quarters, and they balance. Okay. And so you can weigh, knowing the mass of one thing, like for example the silver dollar. Well, suppose you wanted to measure the mass of a silver dollar, you can do that by you know the mass of a quarter now, and on the balance here you can determine that a silver dollar is worth 4 quarters. Now, you can use anything you want for a mass. Okay. In this class, you can use a bolt or a nut or your keys, even a cell phone if you're careful, a spoon or a knife, anything that has a mass. You can use the standard mass. You can use the electronic balance to measure what it is accurately. Now, a better balance, someday in your schoolroom, for example, you just use a meter stick. Okay, here's one long meter stick, and there's a fulcrum in the middle. You can see that's the balance point. You put the meter stick right at the 50 centimeter mark, and then you have some unknown mass on the left. That's some aluminum cylinder, actually, from our 102L supplies. And then you add little weights on the right-hand side, and those are standard masses. They're brass, for example. So you add known masses on the right-hand side until you finally get it to balance, and then you have measured the mass of the aluminum cylinder on the left because you know the masses you stacked in on the right. Okay, so that's how to measure something with a balance or with a teeter-totter, basically. Okay. Now I'll do a small digression here on torques, a more general concept. This thing of measuring, this thing of balancing the two masses on both sides of a teeter-totter with a fulcrum exactly in the middle is a special case. The more general case is you balance the torques about an axis. So you have the fulcrum in the middle. The mass on the left-hand side has a force down, which is mg from gravity, and that force around around the pivot point, which is the fulcrum, will tend to turn the meter stick in a counterclockwise direction. And the masses on the right have a mass mg down, and they'll tend to turn the meter stick around the fulcrum in a clockwise direction. Okay? And the respective torques, the negative torque on the left is minus mg times d, which is the half length of the meter stick, and the torque on the right is a positive torque because it's turning the meter stick around in a clockwise direction, so it's plus mg times d. When these two torques add to 0, then you get a balance, and that's why it works this way. Okay, that's why the simple case is where these two torques add to 0. So that's okay. Now you can extend this concept to any force and any lever arm. That's the value here. Okay, so here now you put the fulcrum at some other place, a very heavy mass on the right hand side with a small distance, little d, small distance, little d to the fulcrum, and on the left hand side you have a small mass with a very large lever arm called capital D. Okay, and so the small mass has a little force F over a long lever arm D, and on the right hand side about the fulcrum you have a very large force, capital F, acting over a small distance, little d. Okay, so now in order for these to balance, as they are in this particular photograph here, the torques, the negative torque on the left and the positive torque on the right have to add to 0, so that the little force times the big lever arm has to equal the big force times the little lever arm, and that's the formula for it. So now, in fact, if you look at this carefully, look at the fulcrum is here, you have a very good millimeter precision on where the balance point is here. Okay, so you can actually measure an unknown mass on the left with a known mass on the right, and measuring the two distances, little d and big D. Okay, and then using this formula. So now this balancing of torques is related to one of the 6 basic machines that are discussed in the textbook, actually. The lever, it's called the lever. So here's a person lifting a very heavy crate with a fulcrum and a teeter-totter, basically, a lever. And by pushing down with a small force, F2, you lift up a large force, F1. Okay, you can lift up a very heavy crate by using a force which is only a fraction of the crate's weight. So here's a puzzle. Here's a girl on a teeter-totter and a man on the other side. So how can this possibly be? So what's going on here is a question. I just found that accidentally on the web one day. Okay, so that's measuring a gravitational mass using a teeter-totter. Okay, basically back to here. It's a teeter-totter, measuring masses with a teeter-totter and more sophisticated teeter-totters. Okay, and that's the gravitational mass. Okay, so now you can also measure the mass with a spring. And so in your folder, there's a very delicate spring. No, it's not delicate, but I mean it's a very weak spring. So-called spring constant is 0.033 newtons per meter. It's a very, very nice spring. And so I did the following thing here. Let me find if I get this here. Let me see if I can do this here. You can see, do this here. Okay. So here is the ruler, the 1 foot ruler. So. And then I cut out piece of the manila folder, okay, from the folder you get. And I rolled it up, and then I forced it into the hole in the one end of the ruler here. And I use that as a support. It's starting to come loose here. I use that as a support for the spring. So the spring is looped over that. And then down here, I made a little cradle, little hoop here, that you could put weights inside of. Okay? And then I had to have something to anchor this to, and I conveniently found I could anchor it to the table I'm sitting on. Okay, but that's a problem. So here you can see that if you put no mass, let me take, this is actually the dollar, the dollar coin. I have to explain a few things here. Dollar coin here. If you have no mass on this, the string is not stretched at all, and you can measure here. You can measure, for example, to the bottom of the spring right here, and read off on the scale where it is when there's no mass on it. Now, if we put in the mass of a dollar here, and then it's going to jiggle a little bit, but if you have it mounted and so on, then it okay. So now you read off exactly the same point here, and it has stretched. Okay, so the mass, which remember has a force down. This mass has a force down, which is mg. And m's the mass here, and it stretches the spring by so much, and you can measure that on the ruler. If we put in half the mass, in other words, put in a 50-cent piece. Where's my 50-cent piece? Oh, that's great. Here it is. Here's a 50-cent piece. And put that in here. It stretches it half as much. Okay? So the stretch of the spring is proportional to the mass. In other words, proportional to the force that's stretching the spring. So that's a property of a spring that's very important. And you can play with it with your hands without thinking. There's no force here now. If I pull with a certain force, it stretches it so far. If I pull with twice the force, it's twice as far. That's a very important property of a spring. So with this now, of course, now that you have it, say, calibrated, that is to say, you know the 0 point, and you know something like 11 grams, and 22 grams. Then any other mass you put on here that lands in between 0 and 22, you just read the scale off, and how much it stretched the spring by, and that tells you what the force is. It tells you mg, and then you know m. So that's another way to measure mass. Okay. Again, it's gravitational. It depends upon gravity supplying the force. Okay. So here is a drawing here. You can see just what I've told you here. And then the stretch of the spring x is proportional to the mass. And the formula is m times g. G is the acceleration of gravity. K is the constant for this particular spring. And x is how much the string stretched. Okay? So you can do that. And you should. It may be a little inconvenient because you have to set things up and so on, but that's okay. In a classroom, you just let the kids figure this out. You ask them, well, how will you do this, or how will you do that, and just let them figure ways to do it. Now, in a regular classroom, when you have, for example, you can see a long meter stick and you have a crossbar. So this vertical bar here is mounted on the, it has a feet on the bottom, so you can put it in. It's heavy. And then with these things here, you can make a crossbar like this. So you see, rather than having this rolled up manila thing, there's an actual aluminum crossbar, which is great. Because now you see you hang a spring. These all springs are the same springs, okay? Here's a spring with no mass on it. You put, for example, 20 grams on it, it stretches this far. You put 40 grams on it, it stretches twice as far. And you can measure it on the ruler. So that's the way you do it. Same thing. And so in a classroom, maybe you'll have access to this kind of equipment, or you can buy it or something, okay? Hopefully. So that's how you measure mass in two different ways, both with gravity. Now, there's another way to measure mass that has nothing to do with gravity. Okay, you might ask, you're on the space station and you're weightless. How do you possibly measure your weight on the space station? There's no net force on you. You're weightless. Okay, so how do you measure it? Basically, you use F equals ma instead of F equals mg. In other words, with F equals mg, we measure the force, and we know g, so we get the mass. But for without gravity, if you measure the acceleration and the force, then you get the mass. This is called the inertial mass. It has nothing to do with gravity. So now this is a little busy. This slide is a little bit busy, but because I have sort of two things on one slide. But you know from your experience, for example, that you push a bicycle. In other words, you put a force on a bicycle. The bicycle changes its velocity. In other words, it speeds up. It accelerates. If you push on a car with the same force, the velocity doesn't change so much, okay? That means the mass of the car is larger, okay? So when you put a force on a mass, the resulting acceleration tells you what the mass has to be. And that's the basic fact here. So now, take for example, take a mass on a spring, and we'll do this next week when we measure time, like building clocks. Put a mass on a spring and let it oscillate up and down. How fast it oscillates up and down depends upon the mass. It doesn't depend on gravity. A similar thing, actually it's conceptually the same thing, is an ice skater. An ice skater has a mass m and is spinning around an axis with a velocity v. So she's spinning around an axis, and the axis is defined by his ice skate pegged into the ice. And his arm is applying a force that keeps her moving in a circle. So that the two arms locked together here, supplying a force towards the center. So now you see you've measured the velocity and the force, and the acceleration of the mass m is the velocity squared over the radius from the pivot point to the center of mass of the ice skater. That's the acceleration. So now you've measured the acceleration and you've measured the force, and so you get the mass. So here's the force is the mass of the ice skater times v squared over r, which is the acceleration. So that's a way of measuring the mass without gravity at all. All right? And I would like to also, you know, something by taking an oscillator like this, and we should do it next week, by measuring the period of a mass oscillating on a spring. By measuring that period, you measure the mass. Knowing the spring constant, you measure the mass. And now that you know the mass of an object without using gravity, you can turn the problem around and measure the mass of the Earth. Okay, so I think we should do that as a problem. It should be a challenging problem. Okay, so that's 3 ways to measure mass. Now what about measuring length? Well, here's a cartoon actually. A boy is having his height marked on the door frame, and by his mother. And he jumps up in the air and he thinks it's a personal best, but mother reminds, no, it's just your height. Okay, so how do you measure length? Well, you know, basic ways of measuring length, and one which I actually use a lot, is my hand span. That's not my hand, by the way, but I know my hand span between my thumb and my little finger, tip to tip. And I can use that now to measure anything I want, okay? If I want to measure the width of a table or how big a piece of paper is, I could just walk my hand across. I just, you know, I can't get the camera right. I walk, I walk and I walk, okay? Count out how many hands I walk with, and I can measure lots of things to an accuracy really of, you know, probably 5% or something like that. Also, your finger width. If you know your finger width is about 1 centimeter or so, okay? With your arm span. Or your pace. A pace is 2 steps. And the mile, and a pace for a normal adult is about 5 feet, okay? 2 paces, 2 steps. And so our word mile comes from the Latin word mille, and it stands for mille pace, which means 1,000 paces, 1,000 paces at 5 feet per pace. That's about 5,000 feet, and that's about a mile. A mile is precisely 5,280 feet. So that's how to measure distances over long distances and over short distances. Now, an artist, you know, holds up a thumb. So on the photograph on the left, it's a pen. You hold up a pen, and you get in the distance. You're looking at some rocks off the coast here. Or on there measuring on the right, you're trying to measure the height of a tree. So you see, by measuring the height little h of the thumb, you can put a ruler there instead of your thumb. you measure capital H, which is the height of a tree far away. And that's because the red triangle that has a base of A is so-called similar to the large green triangle, which has a base of capital A. And the two, so therefore, the ratio of little a to big A is the same as the ratio of little h to big H. Okay, so here's a formula, if you like, for that. Okay, those are called similar triangles. So in fact, an artist is then able to measure the height of a tree, in different parts of the landscape and so on. So that's a way of measuring at a distance. So for example, you can measure the height of a flagpole or a building this way. You can pace off the distance away you are from, for example, a building or the campanile, and then with your thumb, okay, and right triangles, noting the length of your arm, for example, you can measure the height of a flagpole or a building or something. Okay. Now we won't do much of this, but there are areas in volumes, and here are some regular volumes. There's a cube, a sphere, and a cylinder. Those are regular volumes, and there are formulas for the volume of these. If you have an irregular object, for example, here's a screwdriver. If you immerse it in water, the volume of water it displaces is its volume. So in fact, here's a graduated cylinder. The water level is about 160 milliliters, which is a cubic centimeter. And then you put the screwdriver inside, and the water level goes up to about 222 or something, 220 or 222 milliliters. So the difference between these two is the volume of the water displaced, which is equal to the volume of the screwdriver. Okay. Now, so now measuring masses and volumes gives you densities. Okay, an important number to remember is that a liter of water, like you get a liter of water or a liter of pop. A liter of water is exactly 1 kilogram. 1 kilogram, 1,000 grams. Okay, that's a nice number to remember. And a kilogram is about 2.2 pounds. That's the correspondence with the English units. Okay, so here's the end. Play activities with your TA or your critical friends or your future children in the classroom. Measure, and while you're doing these things, think of how you'll be doing this with children in a classroom at a table. And you'll have however 20 or 25 students, and how you'll get them to do these things and encourage them to do them. So here's an exercise. Measure the mass of any object 2 or 3 different ways. Okay? By hand, by a balance, or by spring. And so you measure one mass by multiple techniques, and then you get to compare. Okay? Compare the ease and the precision of each measurement. And then, of course, you use electronic balance to define what the correct mass is. Okay? Another thing to do, useful thing, is to take one object and remeasure it several times. In other words, you measure it, for example, it can be even on the electronic balance. Okay, I mean, it'll probably come up to be the same number every time, but there should be, occasionally it should change. But anyway, you measure a mass several times by the same technique, and then you observe the differences. Okay, and I misspelled histogram here. Make a histogram. So this is one way to measure the accuracy or the precision of a measurement. Okay, so you can do it by the same technique, either yourself or one of your critical friends. For example, you can measure different people measure the same object. Well, the same object has to be something that's common, like, for example, a quarter or something like that. Okay, so by making successive remeasurements and so on, that's one way of measuring the precision of a measurement. Okay. Now, for example, you can measure the thickness of a piece of paper by, for example, stacking 100 layers or maybe 500 layers, and then measure the thickness of, say, 500 sheets of paper, and then divide by 500. That gives you the thickness of a sheet of paper. So a ream of paper that goes into a printer, a laser printer, is, for example, 500 sheets of paper. So a ream of paper is 500 sheets. And then measure something big, like the height of the ceiling or a building. Okay? Now, it's very important here. You're most free to ad-lib on any mass or length you like. Okay? And include this in your video report too. So I haven't talked much about the video reports because I don't quite know yet what they'll be like. I hope you become adept at this. But in a way, think about, in the future, think about while you're doing this, that you're actually going to show this to your future class of, say, third graders. Okay? And they're going to like what they hear, and they're going to understand what you say. Okay? So the essential parts for your TA and for me when we watch your videos is you should describe clearly what you've done, how you've done it, and what's the idea behind it, and also a word or two about how you would adapt this for a future classroom. For example, if you're doing 5th or 6th grade, you might want to do a really good job, for example, of the measuring the mass with a spring, the extension of a spring. You do it once, it doesn't work so well, you develop better techniques, you get better ways of measuring things, and the meter stick and all that. And so with 5th or 6th graders, you can actually ask them to do some real work, so real measurement. But 1st graders, might say it's just a game. What's bigger than, what's heavier than something else, and so on. So use your creativity, okay? Because in many ways in the classroom, your creativity will be very important. Okay, I thank you very much, and I'll see you later today at about 3:20. Okay, I think the Zoom session will actually start at 3, but basically we won't start until 3:20. Okay, thank you, and good day.